Welcome, everyone. For today's prep, we're going to keep looking at that idea of continuity, and we're going to see how to check whether a function is continuous or not from that limit definition. All right, so in this example, we're going to be looking at a piecewise function. So maybe this is kind of a little bit unusual type of a function, but these are actually fairly common types of functions here. And our piecewise function, we're calling it c of x. And kind of think of it as, for this one, there's like two pieces. There's this 100 plus 12x piece, and then there's this 180 plus 8x piece. So the way a piecewise function works is, depending on what x value you plug in, you have to decide which piece of the formula to use. And that's what these conditions here tell you. So if we're trying to plug in a number x that's bigger than 20, in this case, well, then we'd use this second piece. And if we're trying to plug in a number that's greater than or equal to 0, but less than or equal to 20, well, then we're going to use this first piece. And, well, we have the graph of the function right over here. And if we're thinking about continuity, if we're kind of thinking of the graphical, intuitive definition of continuity, we should be able to draw the graph kind of in one continuous motion. We should be able to draw without taking our pen off the page. And that's what this looks like. So it looks like I can start on one end, draw the graph, and I can, we do have a little change in slope right there, but that's okay. I don't have to take my pen off the page to deal with that. So this looks like it's going to be continuous, but let's see how we're actually going to do this from the limit definition. So that if we remember, there's three things we need to check, and all three of them have to be equal. So we need to look at the left-hand limit. We're going to look at the right-hand limit, and then we'll look at the function value directly at whatever point we're considering. So in this case, x equals 20. So we need to check those three things. And if all three of them are equal, then it's continuous. And we're kind of expecting all three of them to be equal in this case, just by looking at the graph. So let's start with our left-hand limit, though. So we're going to calculate the left-hand limit of our function. And again, we're interested in what's going on right around 20. So we're going to approach 20 from the left. So what does it mean if we're approaching 20 from the left? Well, if that's the case, we're using x values that are slightly smaller than 20. So we have to decide then which piece of our piecewise function to use. So we're using x values for our left-hand limit that are slightly smaller than 20. So we go up to our kind of conditions here, and we see which one fits that description. And we see that right here, x less than or equal to 20. So we need to use the first piece of our function for the left-hand limit. So we're going to replace that c of x with actually what our formula is when x is a little bit smaller than 20. And now this limit that we're going to calculate here, this is just a polynomial now, this 100 plus 12x. So we know we can evaluate that by direct evaluation. So we can just plug in the number x is approaching. So in this case, 100 plus 12 times 20. And if we simplify that, we get 240 here plus 100, 340. Okay, so we did our direct eval there. And for our right-hand limit, again, let's write it out, what we're going to calculate. So the limit of c of x as x approaches 20 from the right. Well, now we have to decide which piece of our piecewise function to use. So when we're calculating a right-hand limit, we're using values that are for x that are close to 20, but just slightly bigger. Add a little bit extra. So in this case, x is going to be slightly bigger than 20. So we have to decide which piece of our piecewise function to use. So we go up to our two conditions here, and we see one that fits the description, x greater than 20. So for this, we're going to use the second piece. So then we just want to replace our formula with what that is. 180 plus 8x. So notice I got my limit signs in front. So we're doing limits here. And now we're ready to, now we've recognized what our formula is. This is just a polynomial, so we can do our direct evaluation. So that's the next step here. And we plug in 20, whoops, and we end up with 180 plus 8 times 20, which is, this is 160 plus 180 is a nice 340. All right, so far so good. We've got two of the values. They're both equal. So it's looking like this is going to be continuous. But all we can say right now, based on that the left hand and the right hand limit are the same, is that the limit exists. So this isn't enough to tell us that it's continuous. We need all three of these to actually be equal. So we do need to consider what's going on directly at, and in this case, what's going on directly at x equals 20. So for this, we're going to take our c function, and we're just going to plug 20 directly into it. So this, we're not doing a limit for this one. This is, we're just looking what's going on right at x equals 20. So now we need to decide, again, for a piecewise function, we have to decide which piece of our function fits this description. So we got two pieces here to choose from. And the second piece only works if x is greater than 20. So we don't use this piece if x is equal to 20 or less than 20. So the only one that has an equal sign here is the first piece. So to evaluate this function, we just use the first piece at 20. And if we just simplify that, we get 240 plus 100 is 340. And so what we see here is it looks pretty good. This value is equal to this value. It's equal to this value. So we can conclude, since all three values are equal, c of x is continuous at x equals 20. So with these, we just want to make sure we state the answer. So, you know, we have to put it all together then and state whether the function's continuous or not. And we had to check all three things here. And it's not enough just to show that the left-hand limit and the right-hand limit were equal, because all that tells us then is putting these two together. The only thing those tell us is that the limit of c of x as x approaches 20 in general is equal to 340. In order for something to be continuous, this limit has to equal the function value. What's going on right there, which we checked and it is. All right, so these piecewise functions like this, like c of x, this is a common type of problem for these, you know, checking for continuity, because normally each of the pieces is continuous, but where the pieces kind of come together, it might not match up exactly. And so we need to check for continuity there. So piecewise functions show up in a lot of applications. And normally the pieces themselves are okay. It's where do the pieces actually come together? What's going on? Do they all match up? And that's what we're trying to investigate with continuity here. And we can see from the graph that, yeah, this does match up. We can draw it in one continuous motion without taking our pen off the page there. Let's try one more. This one's not a piecewise function. So we're going to look at example 4. And we're just going to determine whether this function is continuous at x equals 3 or not. So we have this formula here, a rational function. Polynomial divided by a polynomial. It's x squared minus 5x plus 6 divided by x minus 3. And normally when we're checking for continuity, again, there's three things we want to check. We want to check the left-hand limit, and we want to check the right-hand limit. So we want to calculate the limit of f of x as x approaches 3 from the left, the limit of f of x as x approaches 3 from the right, see what we get for each of those. And then we also have to check what's going on directly at. So in this case, directly at x equals 3. So before we start worrying about limits, usually it's easier to start with the directly at, because we're just plugging into the function. So let's actually do that in this case. Let's actually plug right into this function and see what we get. So we're going to take our function 3 and plug 3 into it. So when I replace each of these x's with a 3, what do we get? Well, we're going to get 9 minus 15 plus 6 over 3 minus 3, which is what? 0 over 0. No. Undefined. This 0 over 0, we've looked at that. That's a special indeterminate form. So the limits might exist. So these limits might exist with this 0 over 0 form, but the function value itself is undefined, or DNE. So right away, because the function value is undefined, we're done. This thing is not continuous or discontinuous at x equals 3. So in order for our function to be continuous, the function has to be defined at the point. Otherwise, we have a hole or a jump or something. So in order for it to be continuous, it has to be defined there. So usually this is a good place to kind of just start, especially if you see like a fraction. Try plugging in, and if you get something with division by 0, well then automatically this thing is discontinuous because our function value is undefined. Now for this one, let's just get a little practice here. We should be able to calculate these limits. So let's see if we can factor this fraction here, or the numerator of our fraction. And I think this one factors nicely into x minus 3 times x plus 2. And we're doing the limit as 3 goes, as we're approaching 3 from the left. We see those 2 copies of x minus 3 there, so we can cancel those out. And then this just becomes the limit as x approaches 3 from the left of x plus 2. And now we can do direct evaluation. As soon as we do that canceling, try plugging in again, and we end up with 5. And if you kind of repeat these same steps, you should end up with the right-hand limit as being 5 as well. So what we're seeing is the left-hand limit and the right-hand limit both exist. They're both 5. So our overall limit exists and is equal to 5. But the issue is our function value is undefined. So if we were to graph this function, the graph of this function is going to be really nice. It's going to be, I don't know, some kind of curve. Actually, I think it's a line. It's going to be a line. But then at x equals 3, there's going to be a hole in the graph. Just a point that's missing. So discontinuous. All right, so that'll do it for the prep today. So checking the continuity of functions is going to be important. When we see fractions, we want to think about where are we dividing by 0. And when we see piecewise functions, we want to check to see if all the pieces kind of come together nicely and match up. And so we'll, try another example like this in class. So we'll see you then. Bye-bye.